In this video, we'll cover some key features that characterize functional programming, specifically first-class and higher-order procedures. And in the next video, we'll discuss anonymous procedures as well. So first-class values are any values that can be passed as arguments into procedures, returned out of procedures, assigned to a variable or stored in a data structure, and represented as literal values. Now, in functional languages, functions, or procedures, are treated as first-class values. That is, they can be saved, retrieved, or passed through your program just like any other variable. This is to say that functions are treated just like another type of data in functional programming languages. Now, higher-order functions are those functions that accept procedures as arguments or return them as results. So the two concepts they're linked but they're distinct, where first-class functions is the notion of treating functions as data, and higher-order functions is the functions that do that. They're the functions that have arguments or returns that are themselves simpler functions. So let's see some examples of these things. So let's define some functions. Go to Dr. Racket here, and let's just define foo. So foo of x, and it'll just be a simple function plus x2. So there's a few things to point out even just with this simple function here. So let's run this code. First off is that there's a key difference between just saying foo. If I ask what's the value of this symbol, that refers to the procedure object foo, versus if I say foo1 in parentheses, which says apply that procedure object to the value 1. So there's a key difference between those two things. The symbol itself represents this procedure object, and then we can run that procedure object as a separate notion. Now, let's create a separate procedure here called bar, define bar of y, and that will just say y3. So note that the parameter in this bar function is used as the first element in a combination, which means it has to be some sort of procedure object. It needs to be applicable to its arguments here. So in this case, we need to be passing in, when we call bar, we need to be passing in some value for y that is itself a procedure that accepts a single argument. Okay, so let's try that out. We have such a procedure right here with foo x, so let's run our code and say bar of foo. So if we ask what's the value of this expression, we get an answer. The number 5 is maybe not the most useful though, so let's take a look at the substitution model and see if we can't see how we got an answer. Substitution model. So if our input was bar of foo, again, we want to evaluate both of those sub-expressions, right? Evaluate the sub-expressions and then apply. So if we ask what's the value of bar, we get procedure bar. If we ask what's the value of foo, we get procedure foo, specifically the procedures on lines 3 and 1 respectively. So what that means is we take foo as the argument and substitute it into the parameter throughout the body of bar. So our next line becomes the body of bar, which is y3, where our argument foo is substituted in for the parameter y. And then we evaluate that sub-expression. So in this case, foo of 3, again, we evaluate both sub-expressions. We get foo and 3 are pretty much just themselves, with the procedure and the integer. So we take the body of foo, where the parameter x is substituted for the argument value 3 everywhere throughout the body. And then it's just a simple addition. 3 plus 2 gives us 5. So throughout this example here, it shows the two different key elements we were talking about here, first-class values and higher-order procedures. So the function foo here is used as a first-class value, or a first-class function, when it's passed in as the argument for bar. It's just treated like a piece of data that's passed through to bar, and then the body of bar uses it as though it were a procedure. This makes bar a higher-order procedure because its argument, one of the data types that it works on, is a function itself. All right, so first-class functions, higher-order functions, just like that. Let's see another example here. We'll do this one first. That's fine. Okay, so second notion here is the names of functions don't have any special status to them, right? They're treated like ordinary variables that happen to be bound to something with a function type, some sort of functional value, right? So if I ask what's the value of this symbol, the cross symbol means procedure that does addition. And again, this is schemes or Dr. Racket's representation of a more complex background process. So the thing that goes into this representation, procedure plus, is a little bit more involved than just the thing that does addition. We'll talk about that in future videos. But for now, this symbol is bound to some complex value that represents essentially the body of the function that can do all of that addition stuff. But it is just a symbol. It's just a name bound to a value that happens to be a procedure. So we can do something crazy like define plus to be times. So with the keyword define says take this symbol and associate it with the value of this expression. So the value of this expression is the procedure that does multiplication. And if we associate the plus symbol with that, then what happens if I say plus 5, for example? So normally that would be 10, but we get 25. And that's because we've essentially aliased this plus symbol over to multiplication. So now when we say plus, we're going to get the procedure multiplication. And if we get the procedure multiplication with the arguments 5 and 5, we get 25. All right. Also worth pointing out, I suppose, that if I now say bar foo of, just bar of foo, sorry, the value has changed. We get 6 now. Now why would that be? I'm going to leave that as an unanswered question. See if you can't figure out why is bar foo suddenly different. What is it about this redefinition that affects something way over here? And how does it do it? Okay. So we've seen first class functions, we've seen higher order functions or higher order procedures. One other thing I want to show, because we've seen that procedures can take other procedures as arguments, I also want to show that procedures can return functions as well. So I can say something like define func of x, and I'll just say if greater than or equal to x0, so if x is positive, or at least non-negative, we'll return plus, otherwise we'll return minus. And that'll be the entire function. So if we run this, we can use this by saying something like func of 3. And what will the value of func of 3 be? Well, in this case, 3 goes into x, 3 is greater than 0, so we'll get the true value there, which is the procedure for addition. Notice because I did all the aliasing from plus to times down in the interactions area, that's all been destroyed. So the REPL refreshes, and all those bindings get consumed. If you do bar of foo now, you should get 5 again. Okay, so func of 3 returns a procedure, which means we can use it as the head of a combination. So I could say something like func of 1 with the arguments 3 and 4. And what would the argument, what would the value of this expression be? So again, we have to evaluate the sub-expressions. So this sub-expression, func of 1, is an application. So 1 goes into the body of func as x. 1 is greater than 0, so we get plus back. And this now says plus 3, 4, so we should get 7. Similarly, though, if I said func of negative 1, 3, 4, let's use bigger values, 10 and 5. Negative 1 goes into x. That's now false because negative 1 isn't greater than 0. So we get negative as our answer, or subtraction as our answer. We get minus 10, 5, which is 5. Okay, so procedures can take other procedures as arguments. They can return them as well. This makes them higher order procedures. And procedures can be treated just like data. This makes them first class values in functional languages. So now, this notion of higher order and first-class procedures, it supports another layer of abstraction. So by generalizing patterns not just over different inputted numbers, but over different sub-processes, we can say things in more general ways, and then provide those the more detailed sub-processes on a case-by-case basis as we need them. So let's take a look at a more involved example here. Consider the next few sub-problems, let's call them, and look for a pattern amongst them. So first off, we have compute the sum of the following integers. So if we want to compute the sum from 1 to 100, for example, or between any two integers a and b, we could use a recursive function that looks like this. So given the two values, a and b, where a is the start value and b is the end value, so long as a is not greater than b, what we're going to do is sum up all the values from a plus 1 to b, and then add a to it. So the sum from, let's say, 1 to 100 is the sum from 2 to 100 plus 1. Okay, and the sum from 2 to 100 is the sum of 3 to 100 plus 2. And we get all the way down, the sum from, I guess that'd be 101 to 100 would be 0, and then we recurse down, adding all these up. Okay, so we have this recursive process. It's going to build up all these deferred additions on the call stack, and then they'll all collapse down where the value of a will change once for each iteration because we're going to add 1 to it. So if we want to sum up all the values between a and b, we can do so using a simple recursive function like this. Now similarly, if we wanted to sum all the cubes from a through b, so if a again is 1 and b is 100, we could sum all of the cubes of each number one at a time using a very similar process. So starting from a going up to b, so long as a is not greater than b, what we'll do is we'll cube the current value of a and add that to the sum of all the cubes from the next value of a onward. So the sum of all the cubes from 1 to 100 is the sum of a cubed, or say 1 cubed, plus the sum of all cubes from 2 to 100. And similarly, the sum of all cubes from 2 to 100 is the sum of 2 cubed plus the sum of all cubes from 3 to 100. Okay, so again, we have a recursive process that breaks down this idea, summing one value at a time, building up all the deferred operations. The key difference here is instead of just adding the value a, we're going to cube that value and then add it into our loop. So the deferred operations aren't just adding a single value, they're cubing and adding a value. All right, and consider the next series here. So if we wanted to sum up all of these values, 1 over 1 times 3 plus 1 over 5 times 7 plus 1 over 9 times 11 plus ... Well, first we have to figure out what is the pattern to this system. And it turns out this system converges to pi over 8, so you can actually use it as an estimate of pi if you can compute it. But before we can compute it, we have to look for a pattern. So we can see the numbers on the top are always just 1. The numbers on the bottom are 1, 3, 5, 7, 9, 11. So we can see those are going up by every odd number. And we can see that this value, 1, is exactly 4 less than that value, which is exactly 4 less than that value. So we can presume that that pattern will continue. So 1, 5, 9, 13, etc. And the value here, the second value on the bottom, is always just 2 more than the first value. So if our current value is 1, we're going to multiply that by 1 plus 2, and then the next time it'll be the current value plus 4. So with each iteration, we're going to apply, so we're given some value, let's say 1 as our first value, and given some value 1 as our first value, we're going to take this version of that value, so this function of that value, so take that number, multiply it by itself plus 2, and divide the whole thing underneath 1. So that counts as one individual term, and then to determine the next term, we're just going to add 4 to that value and do it again. So this number times 2 plus that number, all underneath a 1. And again, we get the same sort of value. So what that means is we can separate a few of these pieces out. So we know the term is essentially 1 divided by a times a plus 2, which gives us this. And the increment at each step, instead of going up by 1 as we did in the previous versions, we're going to go up by 4. So with all of these things, they look pretty similar. It might be a bit clearer in this last one if we have a bit of abstraction just to simplify this function. So I'm actually going to grab this function here, bring it over to our racket, and just paste it here. It might be a little bit cleaner if we did something like define some helper functions. So I'm going to say define pi term as all of this. So it takes in some value a, and then it does this calculation. So I'm just going to cut and paste all of that to here. Okay. So for some value a, we're going to say a times a plus 2. And now instead of all of that, we can just say pi term of a, whatever that happens to be. And similarly, I suppose this one isn't as bad, but just to make it consistent, I suppose we'll say define pi next, or pi increment of a to be a plus 4. And then instead of having that there, we can simplify this a little bit as well and say pi next a. Okay. Now the body of our pi sum starts at that if statement, and all of this other stuff happens inside. It just cleans up this pattern to look a little bit more like these other ones, right? So instead of cube a, we have pi term a. It almost looks the same sort of thing. So in all of these cases, in the summing integers and summing cubes and summing this weird pi series, we have a similar pattern. We're summing a series of values, starting from some initial value, ending at some initial value. But in all of them, we're applying some sort of function. In this case, it's the identity function of a, so just a itself. In this one, it's the cube of a. In this one, it's this strange division based around a and a plus 2. In all of them, we have some sort of term here. We need some sort of increment here. In the first two, we have +1s, and in this one, we have +4. So some sort of increment goes here. The ending condition pretty much is always the same. A is greater than b, and in that case, we'll return some initial value 0. And all of these, we're going to build up deferred operations of addition, where we're adding whatever term of a we're using onto the result of adding up the rest of the series. So it's a very consistent pattern, even though these are some pretty distinct series. So what we can do is abstract this pattern into a higher order procedure. And actually that's right here, so let's just grab this one. Okay. So if we wanted to, we could say define just this notion of a general sum between two values a and b. And what we'll do is we'll take in functions for term and next, where term represents whatever function of a we want to apply, and next represents how we're going to increment the current value of a to get the next one. Anything else to say about that? That's about that. Okay, so this sum procedure is a higher order procedure where term and next are first class procedures, or first class functions being passed into sum to being used. And now this means we can use this general version of a sum in order to implement all of these individual type sums without having to recode them every single time. What we will need to code is specific sub-processes, specifically a term and a next function, in order for determining those two parts of this general process. So let's do just that. Let's create a sum that solves this original version here. So let's say define, so for the first thing, for the term, it's just the identity function. So let's actually define identity of x to be just x itself. We need to have some sort of function there. In this case, that function shouldn't do anything. It's just going to map the value to the value itself. So an identity function. And similarly, we have an increment function here, plus a1. So we'll call it increment, or inc of x, is just the current value of x plus 1. So whatever x is, the current value of a will be our x. We're going to take that and add 1 to it. Now, what we're going to do is use this identity and increment functions as the arguments for term and next in this sum. So if we want to do a sum from 1 to 100, we can say sum from 1 to 100 using identity as the term and inc as the next function. Okay, so notice this is not a new function implementation, it's just a function call. In this case, we're passing in identity and inc. Notice there's no brackets around identity and inc because we want to pass the procedure objects themselves, not the results of calling those procedures. So the procedure object associated with identity will be passed into term. So term will now point to that same procedure object. So when we say term a, we're just going to get the value of a because that's all identity does. When we say next a, we're going to get plus 1a because that's what the increment function does. So let's try this out. I'm just going to run the code. So from 1 to 100 should be 50-50, and there it is. All right. So we can define all the other ones as well. Let's get into the cube, I suppose. So the cube function, we're going to need similar things here. So instead of identity, we'll need a cube function, which is pretty straightforward. So define cube of x to be times xxx. And we don't need to redefine the increment. We could if we want, but it already exists, and this is just going to be an increment as well. So we can say now for the cube sum, so this is just the integer sum. This will be the sum of cubes, so sum from 1 to 100 of cube and inc. And this is the cube sum. So instead of identity, we pass in cube, and now for each term, or for each value between 1 and 100, the term will be that value cubed. Run this, and that's the correct value as well. And we can also do this PySum1. We've already created PyTerm and next. We created them as helper functions there, though, so I'm actually just going to make them public here, just to follow the pattern that we're currently using. Depending on your implementation, you probably would keep them private and have your PySum just call sum here instead of re-implementing the sum. But just to fit the pattern of what I'm doing here, I'm going to write it again. Okay, so we'll call sum with 1 to 100, and we'll pass in PyTerm and pi next. If we run this, we should get a value that's 1/8 of pi, or an estimate of 1/8 of pi. So let's run that. Okay. You know what? Just times 8. All of that should give us something relatively close to pi. It's a decent way to verify. There you go. Something pretty close. And if we add some extra digits, even closer. Okay. So that's the idea here. We can create this higher order function in order to support abstraction. So we can just design the process of summation apart from describing the specific sums. And we can leave that specific sum description into whatever implementation needs to use them. So there's no recursion in these new expressions for sum int, right? We could define, if we wanted, we could give it the same name even. We could say define sum int from A to B, and that's going to define two helper functions, and then just call the global sum function. Let's put the bracket where it needs to be for cleanliness. There we go. And now this procedure will work everywhere that the existing procedure worked, this sum int over here. But in terms of creating it, we didn't have to redefine how sums work. Right? We didn't have to reinvent that wheel. We can just call that function to take care of the repetition part, and all we need to do is specify what to do at each stage via these first class functions passed in. So we're expressing these summations at a level that's abstracted away from the mechanical process of computation. We're saying, do summation using these functions, rather than here's how to do summation. So by using these higher order procedures, we provide a way to code the general patterns while abstracting away the specifics of the sub-processes. Okay, that's it for this video. In the next video, we'll talk about anonymous procedures, which are another stage of this, this notion of functional programming using functions as data.